all of you for attending this talk. It's great to be here to speak to you. Allow me to briefly introduce myself. My name is Jordan Moldow. I'm a staff software engineer on the database tools and automation team at Box. At Box, we're building the Content Cloud, a secure platform to manage the entire content journey for enterprises, both large and small. There's three main pillars of Box's Content Cloud. One is protecting your content and offering frictionless security and compliance. Another is to empower your users, who might be employees or end users, to seamlessly collaborate on content, and also to allow your administrators to build workflows around your content. And the third pillar is to connect your business by offering third and second party integrations with our APIs. I'm on the database tools and automation team, which is one of a couple of teams that work on relational database infrastructure at Box. Our mission is to provide highly available, consistent, performant, and easy to use infrastructure for online relational data access at scale. We run hundreds of MySQL instances comprising thousands of hosts spread between MySQL and our data access layer. Today, I'd like to talk to you about a sparse data structure that we created in a recent project for recording denormalizations, in our case, sharding denormalizations. We called this data structure transit nodes, and I'd like to walk you through that today. To start out with, I'm going to demonstrate our use cases and similar use cases that might be able to benefit. I'm going to specify the key properties of the system we built, and then sketch the implementation so that others could build upon it. To clearly set expectations here, there's two things that this talk explicitly is not about. It's not about denormalizations of immutable data. And the other thing is that it's not about denormalizations that require a relational index. So let's jump right into our project's use case. At Box, we have a sharded database system, and we had two key components to the mapping database that allowed us to compute the shard of any object in our system. The first is this sharded key value store that stores child to parent relationships. We think of our relational database as a tree-like structure where files belong to folders, folders belong to users, and users ultimately belong to enterprises. And all of the content for an enterprise lives on a single shard. And storing this information in a tree-like structure of child to parent relationships allows us to traverse this tree very easily and compute shard information as well as other kinds of important properties of the system. The focus of this talk isn't on this database, but the existence of this tree structure is an important foundation for the design that we made, which is why I call it out. The other more relevant part is our legacy mapping database, which this project was aiming to replace. This legacy mapping database was a key value store that stored directly every object shard ID. So you can see in this illustration, we have this enterprise on shard 33, and every other piece of content also lived on shard 33. And there was a row for every single one of these objects where you would input the identifier of the object, and it would directly output the shard ID. We wanted to get rid of this system for various reasons, but one reason that we really wanted to get rid of it was just because of how large the data set was, and we were storing so much repeat information. Some properties to call out of this legacy mapping database is that the mutations are very rare. Most objects just keep a constant shard ID for a really long time. On the other hand, we do require the per record tracking, and I'll show why on the next slide. And we do value that ability to change the shard ID one record at a time. And then the other key property is that we don't need an index. We don't need to find all records that belong on a shard. The use case that requires the mutations is something called the asynchronous cross-shard move, where a user has content that originally belongs on one shard, but then they reassign the ownership to a user on a different shard. So when this happens, this folder, for example, gets reassigned to this user and has to mutate its shard ID from 33 to 92. The asynchronous part is that we now have to walk this tree and move all of the content progressively over to shard 92. And as each piece of content moves to 92, we update the record to change the shard ID to indicate that it has been moved to 92. The end result is a tree that looks like this, where finally every record has been updated to 92. And I'd like to walk through this again, but now in the context of a denormalization. One key aspect of a denormalization is that you have some record where you're storing information that is technically redundant because you actually copied it from some other record. And you can see that here, where every piece of content just copied the shard ID from its parent. So that's one aspect of viewing this as a denormalization. Another aspect is that we want the data to cascade down and stay consistent when things change. And there's two aspects of that. One is that when this folder is reassigned from this user to this user, it now has to inherit the shard ID value from this user instead of this user. So synchronously, we have to update the shard ID of this record to match the new source object, which is this user. Asynchronously, we want the rest of the tree to be consistent as well. So asynchronously, we're updating these denormalizations to match this new chain of relationships. And then this is the eventually consistent model, where once again, everything has the same shard ID as its parent. Most of you have probably worked with denormalizations before, but just to make sure we're all on the same page, I want to briefly talk about some typical denormalization strategies and why we couldn't use them, but where we took inspiration from. The first denormalization strategy is to denormalize the data fully throughout your tree. So you add an extra column to your relational data table, or you add an extra field to your document, and you insert data into it, and you keep it eventually consistent with any changes to your source or your ancestor. You get guaranteed one lookup when you want to get the data, and you can use it as an index in an RDS system. But the data is very dense. This is the least space efficient solution, and it has complications with mutation propagation. But in our case, it was the space efficiency that was the thing that we really wanted to solve. On the polar opposite end, you could just not use denormalizations. It's very space efficient, but it's very computationally expensive to read the related data. So that was a no-go for us, especially since this doesn't allow per record mutations, which was a key requirement for us. If you have immutably denormalized data, that's also pretty straightforward to do, because you can store the data in a cache. If it's in the cache, you return the data. If it's not, then you compute the answer, put it in the cache for next time, and then return it. You get very fast repeat reads, and instead of using disk, you can use cheaper cache. But that doesn't really scale to a mutable design. So it works really well for immutable designs, but mutable designs, now you have to think about, how am I invalidating cache? How am I avoiding corruptions and thundering herds? And your design is going to have to be very domain specific. So we wanted to take inspiration from the immutable design, but we still had to handle this immutable case, but we also wanted the space efficiency. Let's start to sketch out what we might be able to build. So We use SQL, so I'm going to speak in those terms. We want a sparse data structure, so we're going to create a separate table to store the additional data that we need. And that table is going to be empty by default. In the steady state, our state is going to be computed recursively and cached rather than using up space in the table. But when necessary, we'll materialize state in the database table when necessary in order to record things where the cache is not sufficient. And the rest is going to need to be fleshed out more. The strengths here of this half-baked idea is that we're going to get sparse data storage, aggressive caching, almost always O(1) read time. In most of the case, it's going to act like an immutable denormalization strategy, but we're going to build in the flexibility for an occasionally mutable and therefore durable denormalization strategy. And some questions we want to answer by the end are, how can we build a system like this that's consistent? In this system, what kind of cache invalidation are we going to need to make sure the data stays consistent? How are we going to recover if our cache is flushed and we're starting from scratch? And as this sparse data structure grows and grows, are we able to garbage collect that data to keep the data size from growing and accelerating? Here's key insights that we built up in order to finally arrive at the final transit node solution. The first key insight, which I've mentioned a couple times already, is that at rest, this acts like a normal cascading denormalization, where all of the data inherits from its parent all the way up to the top. And additionally, when we're at rest, this looks immutable and it acts immutable. So we can use immutable style caching. So we can create a cache where the cache key is just the object identifier and the cache value is the shard ID value. And so if we're looking up folder 82, we just see in the cache, it is on shard 33. If we're looking up folder 83, that's not in the cache, but we see that its parent is folder 82, which is in the cache. So that gives us the value of 33, which we can now put in the cache. However, the cache isn't going to be sufficient. In the intermediate state, we saw that one node can be on shard 92, for example, while its children are still on shard 33. And so we have a problem where these, if they were to inherit a cascaded value, they would get the wrong value of 92. So we need some additional state besides what was in that cache in order to record this state. And so we're going to either need to store additional state that's associated with this node here, or we're going to need to store additional state that's associated with these nodes here. And similarly for here, where this, if it were to cascade, would get this value, this, if it were to cascade, would get this value, and so on. So there's really a lot that could go wrong if we don't make things durable. So again, either these 33s need to be stored in the database, or these 92s need to be stored in a database. On the other hand, while we're going through this traversal, there's some things that don't need to be in the database yet. We see this part of the tree here that hasn't moved. All of these things are still supposed to be on 33, and so is this node here. And so these nodes can continue to receive the cached cascading information from this node. The other thing I mentioned earlier was that we don't want to have to traverse the tree twice. And so if we are adding durable state as we traverse, there's actually only one place we can put it. We can only put it on the nodes that we visited already. So in this case, we visited this node and these two nodes in order to update them to shard 92. Therefore, these three nodes are the ones that must have the transit node information on them. And these nodes, on the other hand, do not have transit nodes on them. So they receive transit nodes as they get updated. So that all combined is going to lead us directly into our transit node definition. Here's the transit node definition that we settled on in our own MySQL design. We have this extra database table, as I stated before. Its primary key is going to be an object identifier. So it's a key value store from an object identifier. And then the target information is going to be these two pieces of data, what we call the shard ID and the default descendant shard ID. The definition of the shard ID is that it records data that short circuits this record's shard information. Whereas the default descendant shard ID, sometimes abbreviated DDS, is going to short circuit the shard calculations, not for the node itself, but for its unvisited descendants. And the way that this information gets used during a cross shard move is that if a node has already been moved successfully, it's going to have a transit node on it, and the shard ID value is going to give its shard value. On the other hand, nodes that haven't moved yet are not going to have a transit node on them, and therefore the first ancestor with a transit node is going to have a DDS value that gives it shard. Here we're going to talk about this in pictures, and I'm adding a new notation to our pictures. Before, we were using bolded colored information to represent shard information. We're still going to do that, but now we're only going to use the colored information to represent durable data in MySQL. And we're going to use gray numbers to indicate values that are either cached or just calculated. And so here we can see what our cache is going to look like at rest, where we have cache keys for each identifier, and we can cache the shard and the DDS value as well. So here's what the picture is going to look like if we just look at shard IDs. And here's what the picture is going to look like if we also add these new DDS values as well. So in the steady state, everything is just equal to whatever the root has, which is 33. On the other end of the spectrum, if we perform a move and we allow it to run through to completion, every node in this tree is going to eventually get a durable transit node, and it's going to record the shard as 92, which was the final state, and the DDS is going to match what it was before, which is 33. And the reason for that is because if we're only partially in progress, these gray nodes are going to be exactly the same as they were before the move. And in order for them to be the same as before the move, they need to recurse up to a persisted DDS value that equals 33. Hence, the shard IDs get set to 92, which is the destination, but the DDS values stay equal to 33, which was the source. If you prefer pseudocode instead of pictures, you can think of it like this. If you're calculating the shard ID of a record and it has a transit node, then you return the shard ID on that transit node. Otherwise, you're going to recurse up to the parent and calculate the default descendant value of the parent. And to do that, you again look for a transit node. If there is a transit node, then you return the default descendant shard ID value. Otherwise, you're going to calculate the inherited value. A very important part of this design is the invariance that this system provides. So let's dive into that. There's something that we created that I like to call the golden rule of transit node operations, which is that when you're operating on a record, the shard ID for all other records in the system doesn't change. And the default descendant shard ID for all other records in the system doesn't change. What might change during an operation is just the properties of the record itself. So when we're doing a cross-shard move on a record, we're going to end up changing the shard ID from 33 to 92. And so that's when the shard ID can change. But as you can see here, when moving from the left to the right, the DDS also remains invariant. So when are we allowed to change the default descendant shard of the record itself? We do need to be very careful about that, because in general, you cannot change the DDS without impacting the children. If you look at this picture here, these descendants are supposed to be on 33 at the present moment, and they don't have their own durable data. Therefore, they are depending on this DDS value being invariant for the time being. So in general, we cannot change the DDS value. Updating our list of invariants, we're going to say that during an ordinary operation on a record, the default descendant shard ID can't even change on that record. So the only time the values do change, shard ID can change when the record is cross-shard moved. And default descendant shard ID, we're going to say, can only change during garbage collection. Before we get into the operations, there's one special operation I want to call out, which is this idea of materialization. It's a very simple operation, and this is basically just persisting the inherited values that already exist. So what you do is you create a brand new transit node, and you set the shard ID equal to the computed shard ID, and you set the DDS equal to the computed DDS. This is the full table of invariants. The materialize operation that I just talked about, by definition, is invariant in both, since it places the computed values into the transit node. When we're changing the parent of a node, that is also going to be completely invariant, because before the move, we materialize a transit node on that thing being moved. And the reason that we do that is to protect against race conditions that could happen if other nodes in the system are being inserted or garbage collected concurrently. The moving record to a new shard, updating the denormalized value, that is definitely going to change the shard ID value. And what happens there is we do materialize a transit node, then we immediately update its shard ID to the correct value. On the other hand, we already talked about how the DDS value stays invariant during that operation. Inserts and deletes are going to be a bit dependent on your implementation details. So I'm not going to go into them too much in depth. Garbage collection is also going to be implementation dependent, but here's some considerations for that as well. We do want to keep shard ID invariant, and default descendant shard ID doesn't need to stay invariant, but the default descendant shard ID of all the other records definitely needs to stay invariant. So we need to perform validations to make sure all three of these invariants are maintained. And we can split that into two different kinds of validations. One we call upwards validation, and it's to check whether we can maintain the shard ID invariant on the node itself. Here's three different scenarios to illustrate that. In this case here, we want to see if we can garbage collect this node where the shard is 92. We cannot do that in this scenario because the shard ID doesn't match the DDS of the parent. And if we were to delete this transit node, it would now be inheriting a different value, and it would break that invariant. On the other hand, in these two situations, the shard ID does match the parent DDS, and so that invariant will be maintained if we were to garbage collect this transit node. The other aspect is the downwards validation. Can we make sure that we're maintaining DDS of the descendant shard, the descendant nodes? And there's two different scenarios to consider for that as well. One is when the case is that we can maintain it. And so if you look at this node here, if we deleted this transit node, that wouldn't be very good because this node down here is currently expected to compute a shard ID of 33. But if you deleted this, it would now be computing a value of 92. So that's no good. On the other hand, in this scenario, the DDS and the shard IDs of all of these nodes are the same. And so if I remove this, there's going to be no impact here because this, when you delete the transit node, is just going to have the same gray values as this, which is the same values that it already has. So deleting the transit node is going to have no impact. So you can do that safely. On the other hand, if the transit node that you want to garbage collect does not match the parent, it might still be possible to garbage collect, but you have to be a little more careful. In this case, you definitely can't garbage collect it, because if you did, then this computed value here would change from 33 to 92, which is not acceptable. On the other hand, in this case, we can garbage collect this transit node. And the reason for that is that the DDS value is unreferenced. What I mean by that is that the sole child here has its own transit node. So garbage collecting this won't impact this because this one wasn't using this DDS in its computations anyway. The other thing we have to be mindful of is concurrent inserts, which is what this dotted circle is meant to represent. The reason that this is okay is because we're assuming that our insert implementation in this scenario is going to materialize a transit node. So even in this scenario, the DDS value is going to be unreferenced, and so it's safe to garbage collect it. And that's the end of the rough sketch. Here's some results. We had these questions that we established at the beginning of the talk. Will this have any consistency problems? We haven't run into any consistency problems in production. The invariants that we created are extremely powerful for ensuring consistency in our system. And that's related to cache invalidation. The second question was, do we need cache invalidation and what's it going to look like? We never ever change the DDS value, remember that. And so we never need to invalidate the DDS value during normal operations. We only need to invalidate it right after garbage collection. Shard ID, on the other hand, for simplification, we decided not to even cache the shard ID so that we wouldn't have to worry about invalidating it during the cross shard move operations. So we just didn't cache the shard ID. For cache flush recovery, we were actually really thrilled about this. When we did cache flush tests, we found that there was barely any observable impact on the overall latency in the system, and there was no minute over minute impact to the cache size. So we saw that the cache size actually recovered very quickly after a cache flush. But that could depend wildly on the kind of traffic patterns that you see in your system. So don't take that for granted. And then we found that garbage collection was achievable and not too complex. To conclude out the talk, we had a use case where we had something that was denormalized, where it wasn't fully immutable, but the mutations were rare. And we couldn't do a caching only solution because we needed the explicit per record mutation where we needed to do a one-phase traversal through all the content. And we didn't need an index. We didn't need to index on the shard ID, so we could explore solutions other than putting the data in an extra column. But we wanted a solution that would be space efficient and almost always O of 1 read time. And if you have a use case that matches this, this could potentially be a great option for you if you're trying to migrate off of an existing mutable, non-indexed cascading system. On the other hand, if you don't have that key requirement of having that explicit per record mutation, it might just be simpler to use a caching only design instead. And so this definitely isn't a one size fits all solution. It has that specific niche where you need to do that per record mutations. And that's it for the transit node system. Thank you so much for attending. I hope it was valuable to all of you. and I hope you have a great rest of the conference.